Hey Alchemy University, welcome to Module 1.3. Today we'll be introducing mining and proof of work, starting with mining. 3 key points. First of all, the definition. Mining is the process of creating a block of transactions to be added to a proof of work blockchain. So here we have a very simplified high-level view of a blockchain of 3 blocks. Mining is literally just the process of extending this chain with a new block. Number 2. Peers in the mining process are called miners. So here on the right-hand side, we have a very simplified view, high level of a blockchain network. Just a bunch of nodes, aka computers, interconnected together. So who are the miners according to the network? Well, to distinguish that, we have to take a lower level view of this exact blockchain network and realize that all of these nodes run differing software processes each that help the network function and run. So to the network, a miner is just any of the nodes that contains miner software processes, right? So who are the miners according to other humans? Because you can go up to someone at an Ethereum conference and they'll tell you, hey, I'm an Ethereum miner. What does this mean? Well, it's just the human that set up the hardware that runs the software in these nodes, right? So they can also be considered miners. Leads us into our third point. Mining, at the end of the day, is just an automated software that people run. There's no human element to mining except the setup and maintenance of the hardware required to do it. So mining as a whole has 2 main functions. Number 1, and the most important one, is that mining is responsible for the enforcement of consensus rules in a blockchain network. So consensus rules are what a blockchain network lives and breathes by, right? Distributed and decentralized networks have the issue of how to agree on what is valid and what is not. And the way these blockchain networks solve it is by establishing consensus rules. These are the rules that guide the decentralized and distributed network to agreement on what is considered actual valid state. So I've actually linked a block of source code from Bitcoin Core. This is the exact same software or the exact same lines of code that verifies that any potential new block, this function is called check block, this function verifies whether any block that is being proposed to be added to the Bitcoin blockchain to extend the blockchain to be mined, this function verifies in an automated way that that block adheres to the consensus rules of the network. It's all automated. As a consequence of this, usually to incentivize miners to actually expend the energy to add security and enforce consensus rules in a network, usually to incentivize these miners, they get a part of the network's currency issuance, a part of the network inflation. So this isn't as important. But it's a consequence of the first and more important one, which is the enforcement of consensus rules. So how is a miner actually rewarded for their efforts? And this leads me into the second topic, proof of work. So a miner has to present some sort of proof of work to the network that proves that they did valid work in order to actually get a cut of that currency issuance. So just to recap, proof of work ends up just being a consensus mechanism. So this is the mechanism that the consensus rules are enforced by. So again, this is how decentralized networks like Bitcoin and Ethereum decide what is considered valid or not and who can add new blocks. You want to add a new block to the proof of work blockchains, you need to present a valid proof of work. So this valid proof of work actually ends up looking like the solution to the mining process. That is actually the proof of work. And how do you get that? Well, the mining algorithms, the mining software in the nodes actually try to find a valid proof of work for miners continuously, 24/7. So leads us into the question, for proof of work mining, when a miner mines a block, what is that miner actually doing? And the answer is, well, the mining software automatically just repeatedly hashes a bunch of data, usually this data being new transactions to add to the blockchain, until a hash output is found that meets a certain target difficulty. So we can actually kind of replicate this a little bit. So the proof of work mining algorithm looks just like this. You have to And this is all done automated by the miner software, but we're just taking a look at what that actually looks like, what the algorithm looks like. So first one is to take the current block's header. So if we're on a blockchain and the last block that was mined by the network is block number 111, then the mining algorithm sets forth that you have to take that block header, the block header of block 111, and start creating block 112 as part of the mining process. So it says here, take current block's header, append the nonce starting at nonce equals 0, hash that data, run it through a hashing function, and check whether the output matches or is below a target difficulty, usually provided by these proof of work blockchain networks. If the hash is lower than the target difficulty, then you've solved the puzzle. That's perfect. You have a valid proof of work that you can present to the network for you to get rewarded from that currency issuance. If you didn't find a proper hash output, you just restart the algorithm from step 2, but increase the nonce by 1. So if this all seemed a little too wordy, maybe let's try it. So I actually got here a link to a SHA-256 hashing tool, and let's say the current block is 751,763, right? So let's say that's just the last mined block on the network, and that block's current header is this big long hash digest. So typically what happens is we are asked to hash together or input a bunch of this data. So we take the pref block header, right? Just number 1, append the nonce to it. We'll append the nonce starting at 0, and then potentially also as well add transactions. So this is what our actual candidate block looks like. We're actually setting up everything necessary to actually perform mining. So this is the hash output that we get. Anytime we change any input in here, that hash output is recalculated entirely. So we've gone ahead and established a pref block property, and we've added our own data, right? We're just adding kind of dummy transactions to simulate what us building out a candidate block would look like, and a nonce. And literally, this is the revelation moment. Literally, all miner softwares do all day is starting at nonce equals 0, linking the pref block, and they just increase the nonce by 1. Okay, and that changes the hash output to 98 DEF2, etc., right? So that is what is actually kind of compared against the target difficulty of a network. So you'll notice Bitcoin actually has a pretty impressive target difficulty. It has 19 leading zeros at the moment, which means it's incredibly difficult to find a valid proof of work in the Bitcoin network. So this is all we're comparing. The hash output against a target difficulty usually provided by the protocol. So in Bitcoin's case, if you want to add a block, you need to find a hash output given proper valid input that is under a target difficulty. In this case, finding a valid hash for Bitcoin and being able to mine a block onto the chain and get rewarded would mean finding a hash output with at least 19 leading zeros. So very difficult task. Just finding one leading zero will take us on average 16 tries. So this is the revelation moment, by the way. This is all miner softwares do all day. They just go 10, 11, 12. They just increase. Oh, we found the double zero in there. So that was 13, right? 13, 2 leading zeros, not bad. But miner softwares will do this thousands, trillions of times a day in order to, and just every time they increase the nonce, they're checking, did I find 19 leading zeros? Did I find 19 leading zeros? No? Okay. And say someone beats you in the race and they find this new block. So remember we were saying, you know, if this chain had like the most recent block being block 112, if someone else finds block 113, then that means you've lost the race, right? But that doesn't matter because you just update the pref block property to that new block, right? You link it to the newest block, still following this algorithm, and again you start at 0, right? And again you start mining. This is all mining is. This is literally all mining is. I'm as slow as it'll get. Some of these hardware machines will do millions of these hash output calculations a minute. So that's all mining and proof of work ends up being, just the running of an algorithm. So just a TLDR, proof of work ends up just being the consensus mechanism by which proof of work networks like Bitcoin and Ethereum enforce the consensus rules. This solves the Byzantine generals problem, which we have a separate video linked for. And then for the last point, mining is a function of proof of work, of the proof of work process, and it's meant to secure a network against fraud. So all that happens is miners race to find this valid proof of work in order to get compensated, right? And that valid proof of work just ends up being either a bunch of leading zeros, a hash output under a target difficulty, and then once you find it, presented to the network, you get rewarded for your efforts. And that's it. Tune in next time for blockchain network architecture.